Hello and welcome to another video on Real Analysis 4. Today we're going to be covering Moore-Osgood Theorem. So let's get straight to it. So what's the claim? Let x0 be the an endpoint of some interval j. We remark that x0 could be, it is an element of the extended real number line, meaning it possibly could be a positive or negative infinity. Let fn and f, where fn is some function sequence, be such functions that they map the interval j onto the real number line, and let them satisfy the following 2 points. 1. So we require that fn converge uniformly to f, and 2, that there exists the limit as x approaches to x0 of fn, and it is equal to an, and that it is real. So this one cannot be infinity, it just must be real. For all natural n, then the limit as n approaches infinity of an, and the limit as x approaches x0 of f of x, where f is the function to which fn converge uniformly, exist, and they're equal. In other words, the limit as n approaches infinity of the limit as x approaches x0 of f of n of x is equal to the limit as x approaches x0 of the limit as n approaches infinity of f of n. These two limits may be swapped if fn converge uniformly, and if the limit as x approaches x0 of fn exists for all n. Alright, so let's get to the proof. It's not trivial, but it's not that difficult either. So, by the Bolzano-Cauchy criterion for uniform convergence, or BCC2 for short, there exists, so by this theorem, the fact that fn converge uniformly to f is equivalent to saying that for all epsilon greater than 0 there exists some natural number n0 for all mn greater or equal to n0 for all x in the interval j. It holds that the distance between fn of x and fm of x is small. Alright, but if you really think about this, we can take this expression to the limit of x approaching x0, and it will still make sense and will be still well defined, because x0 is the endpoint of the interval, and therefore is included within. So the functions will be well defined at x0, right? So taking both sides, to the limit as x approaches x0, we get, for all epsilon greater than 0, there exists some n0 for all n greater or equal to n0. We now have a specific x, we no longer write for all x in j. It holds that fn of x0 minus fm of x0 is smaller than epsilon, but this is the definition, this is simply the Bolzano-Cauchy criterion. So by Bolzano-Cauchy applied to the fn of x0 sequence of real numbers, so we get that fn x0 approaches f of x0, which is equivalent to saying that the limit as n approaches infinity of an is equal to a, by our definition up here. But I've said that the endpoint needs to be in the interval. That is not true. This argument would hold still even if it were not. Even if J were an open or semi-open interval and we're dealing with an endpoint which was not actually included in it. Why would it work? Well, precisely because of this requirement, number 2. We simply require that the limit as x approaches x0 of f of n of x is equal to an, and for it to be real. So it would still work. It would still work, absolutely, and I suspect it will be much more useful in this form. All right, so of course we are taking n to infinity. So this is if x0 is an element of J, and if it isn't, then we would have that the limit as x approaches x0 of f of x as n approaches infinity converges to the limit as x approaches x0 of fn converges to the limit of f of x. In other words, the limit as n approaches infinity of the limit as x approaches x0 of fn of x is equal to the limit as x approaches x0 of f of x. But of course this is nothing else than the limit as n approaches infinity of an by our purple definition above, and we claim that this is equal to some value which we denote a if x0 is not in J. Okay. Well, okay, so we have demonstrated that the limit as n approaches infinity of the limit as x approaches x0 of fn of x is equal to a. We now wish to show that the limit as x approaches x0 of the limit as n approaches infinity of fn of x is also equal to a. In other words, that these two are equal, as we claim. Well, how shall we do this? Well, beginning by saying that epsilon is some some arbitrary value greater than 0 would be a good start. Now, by definition of uniform convergence, we have that fn converging uniformly to f implies that there exists some n0 again for all x in J, such that fn0 of x minus f of x is smaller than epsilon. Okay. For all n greater or equal to then 0, and 0, of course. And it will also hold then a n 0 minus a is smaller than epsilon. A n are a convergent sequence, meaning that there will exist some n1 such that for all n greater than n1, the difference between a, the limit, and a n will be smaller than epsilon. The same thing will apply to this left-hand side. We again can find some n2 for which this will hold, and we'll simply take the greater of the two n's, either n1 or n2, and then both conditions will work for all n greater than their maximum, then the greater of the two n1, the greater of the two n's. So again, nothing clever. Well, okay, let us have then a fixed function f and 0. n0 is fixed, so there's no issue. And the limit as x approaches x0 of fn0 of x, we shall denote a n 0. Very well. Well, from the definition of limit, this implies that there exists some delta greater than 0 for all x in the punctured neighborhood x0 delta intersected with j, just a precaution, such that the distance between f and 0 of x and the limit point a n 0 is small. Now, for all x in the punctured neighborhood x0 delta intersected with j, it holds. And now we shall demonstrate our final claim. We shall show that f of x and a are close. In other words, we will have demonstrated this limit, which is precisely what we want. Now, we want to show that they are distant, that they are not far apart. So, f of x and a. Well, this is by the triangle inequality, certainly smaller or equal to the following sum. So we will have f of x minus fn 0 plus fn 0 of x minus an 0 plus an minus a. Alright, we certainly could have done this. To see this simply, we can see that these terms cancel out. So we could say that this is actually equal to the absolute value, where we have the individual components inside the absolute values together, and we would see that it would cancel out to give us again f of x minus a. Nothing clever. But what is clever is that we have already prepared ourselves some estimates for these things. So, for example, this term we have right here. Right here. This term, well, we have it straight over here. And finally, this term, we have right here. So altogether, this is smaller or equal to 3 epsilon, because each one individually we know is smaller, strictly smaller than epsilon. So altogether they are strictly smaller than 3 epsilon. Meaning we have shown that f of x minus a is very small indeed for all x in this punctured neighborhood. This means then the limit as x approaches x0 of f of x is equal to a, but this is nothing less than Well, that's not important. What is important, however, is that this is the same as saying that the limit as x approaches x0 of the limit as n approaches infinity of fn of x is equal to a, which we know from the previous result is also equal to the limit as n approaches infinity of the limit as x approaches as x0 of fn of x, which concludes the proof.